Okay, so we're going to be doing a lab today to look for the coefficient of friction for these ramps. They're supposed to be next to frictionless, but we're going to see how true that is. All right, so the way we're going to be doing that is by looking at some photo times compared to different angles for the ramp here. All right, now on your lab sheet that is in the folder, it has you filling out the angles of each of these. All right, when you're looking for your angle, we're going to be basing that on the angle of the ramp, because the angle that you use in all of your component vectors, like your parallel and your perpendicular forces, well, they match up at a similar triangle to the ramp itself. All right, luckily, one dimension along this ramp is already a known quantity. These ramps have a length of 1 meter, so we do know the hypotenuse. All right, so from there, for each of our data points, we're just going to be measuring the height of this ramp, because that's fairly easy to measure, with one small caveat. All right, if we measure the height of this ramp, okay, so currently the ramp goes up to a height of about 48.5 centimeters, okay? The issue with that is that the base of that ramp does not exactly touch the ground, okay? So for this, I'm going to be taking a measurement up to a point on the ramp, and then I will take a measurement up to that point down here and subtract the two, and that will give me the total height of just the ramp without that little gap of space down there. Okay, so let's get our data points. The other thing we're going to be measuring is the photo time. All right, so we're looking for the final speed at the bottom of the ramp, which means that this thing is on gate mode. It turns on when the post enters and it turns off when the post leaves. Okay, so when we're looking for our final velocity later, that's just going to be the width of the post divided by the photo time. Because it's covering such a small distance, we can assume that the acceleration for that 1 centimeter is 0. It's an approximation, but it's good enough for us. All right, so the distance you're using here, that is going to be 0.01. That is the width of those posts, and then the times, well, that's going to be whatever we end up getting for our photo time for each data point as we're letting it go down. All right, now that thing did say, hold on, I need to check that actually. I believe the lab is letting the cart go 0.5 meters. Yes, okay. So the cart is going to be traveling 0.5 meters. You're going to be using that later to find the acceleration there, okay? But we'll be dealing with that later. All right, so first off, let's get our dimensions for this. All right, each trial we're going to remove 2 books from here, and that will be changing the height of our ramp. So our first data point, we've got, okay, 48 there, and then this one. Okay, so height of our ramp is just going to be 44.7 centimeters for our first data point. Okay, so you're not recording those heights on your data table, it's looking specifically for the angle. All right, so we've got our opposite side, and then your length for each of these is going to be 1 meter. So we've got opposite and hypotenuse, so you're going to be using sine to figure out what angle corresponds to that. Okay, so we've got an opposite side of 44.7 centimeters. We've got a length of 100 centimeters. Figuring out your angle using sine from that. Now, let's get some data. Okay, so turning on our photo gate, we want it to travel 0.5 meters. Okay, so right now this photo gate is over the 30 mark on my track. So I am going to be starting the gate, or starting the post from the 80 mark. Okay, so this cart will travel 0.5 meters until it gets to our photo gate. Make sure it's perfectly lined up, and here we go. Nice. All right, so that gave us a photo time of 0.0052. Now, when you're looking for your acceleration later, just remember that this photo time is not the time it took to go down the entire ramp. This photo time is used exclusively for finding the final velocity of your cart. All right, that is only how long it took to go 1 centimeter. All right, so there's our first data point. We've got a height of 44.7, which we'll use to find our angle, and we've got a photo time of 0.0052. Now let's change our cart. All right, we're removing 2 books so we can have a more significant change in angle. Okay, and we're going to measure our new height. Okay, so now we've got, and this angle will change ever so slightly. All right, so now we're looking at a height of 38 centimeters. Okay, so your height has changed on your triangle. Your hypotenuse is still 1 meter because the length of the ramp has not changed. All right, so now sticking our post back on, putting the spring back in. All right, we're going to make sure that our photo gate is right above the 30 because we did move the ramp a little bit, so we might need some adjustment. And making sure that our post is at the 80, so it's still traveling a total of 0.5 meters down the ramp, and letting it loose. Okay, so that gave us a photo time of 0.0056. 0.0056. Okay. Got our second data point. All right, it had a slightly longer photo time, which makes sense because this thing isn't as steep anymore. Less of your acceleration due to gravity is pointing downward. So you would expect a longer time to get through that photo gate. Moving another 2 books for data point number 3. Okay, and measuring our stuff. Why do I always look at it upside down? I feel like by now it should actually work out. All right, so we've got 34 and okay, so we've got a length, or no, a height of 30.7 centimeters this time. Okay, so we can use that to find our angle again. Our length is still 1 meter. We're going to adjust this because our ramp did move. Make sure that it is above the same mark as before. I'm going to lower it down a little bit because our ramp is lower. I want this thing to still engage as the post goes through. Let's make sure that this is a good height. Oh, it's perfect. Right on. All right, so got our photo gate set up. Setting this 0.5 meters away. So it's still traveling the same distance each time. It's just looking at a different angle. And letting it go. Okay, so this one we ended up with a photo time of 0.0063. Okay, so again, with less of our gravity pointing in the direction of its motion, its acceleration was smaller, gave it a larger time to get through the photo gate. So as we remove angle from this thing, it's going to be getting slower and slower. All right, removing another 2 books. Here we go. All right, and pushing things over, making sure that it's easy to measure our distance. We've got a height of okay, so we've now got, how did that end up being higher? Hold up, I must measure something wrong. I did measure something wrong. Yeah, it's 27, not 37. What a dingus. Accidentally added 10 centimeters to this thing out of nowhere. All right, so now we're looking at 24.1 centimeters for our height. All right, so you can find your angle, again, using sine. You got your length, you got your opposite side. Let's make sure that this is properly set up. We've got it right over the 30. I'm going to lower it down some more so that the post still engages it. Where did I put the cart? There it is. sure that that thing, there we go, perfect. And putting this up 50 centimeters above it and letting it go. Okay, so this one we've got a photo time of 0.0068. Again, increasing in time. It'd be really confusing if it went faster one of these times. All right, last data point, removing 2 more books. Getting pretty close to a horizontal surface here, which means that less and less of our gravity vector will be pointed in the direction of motion, meaning it will be accelerating us. Okay, so measuring a height again. This time we've got a height of 22. Okay, so this one we've got 17.3 is our height. Okay, last data point. Making sure that this is above the 30. Lowering it down some more. A little bit too low. Raise that up just a skosh. And the 30. On. And bring that up to the 80. Resetting. Letting it travel 0.5 meters. And okay. So that one gave us our largest photo time yet, 0.0082. That one seems a little bit larger than I was expecting, just based on the increase that we've been getting for the other one. So I'm going to try that one again, just in case. Make sure that our data actually matches up. All right, so letting go 0.5 meters. 0.0082, right on the nose. Okay, so this is all of the data that we actually need to collect. All right, the other information in your table. So finding your final velocity, you can just use the photogate equation, taking 0.01, the width of the post, and dividing it by each of your photo times. When you're looking for your acceleration down the ramp, okay, so we're looking for A. The information that we'll know will be VF. That will be whatever you're getting from this. You will know the distance down the ramp. Remember that we're looking at the entire distance that it traveled, not the entire length of the ramp. All right, we're looking at 0.5 for that distance there. All right, and then the other thing that we will know is, initial speed. Initial speed of 0 meters per second. Okay, so once you've got your final velocity here, you'll know distance, initial speed, final velocity. Looking for acceleration, you're probably going to want to use your formula C to solve for that acceleration. All right. After that, on the back side, when you're looking for all of your forces, well, we've got our angles. Once you use sine to figure those out, so you'll be able to use mg sine theta. I forgot, there's one more thing that we need to find, because we do need to know the mass of this cart to figure out all of those component forces. All right, so let's just move this stuff out of the way. Get a triple beam balance up in here. All right, that thing actually calibrated right. A lot of my triple beam balances are pretty garbage. That's a little bit high. Okay, so we're just gonna... Weird surprise cut. So, had someone come in, continued getting the mass of this thing. Balanced out at 261 grams for our car. So, when you are using your mass to find your forces, make sure that you convert that into kilograms. All right, so 1,000 grams in a kilogram, multiplied by 1,000. All right, so from there, it's just like a problem that you would have on any of the other ramp sheets that we've had so far. All right, so use the forces that are on that car, figure out what we got for our coefficient of friction. You're going to need to calculate your friction force, look at your net force, how much total you have, think about what direction things are pointing. Still be a good idea to draw a diagram. They're always helpful. Ultimately, our goal is to find mu, so you're going to need to find your friction force and your normal force. Luckily, we have ways of finding both. All right, so if you run any questions on it, make sure that you send me a message on Schoology. I can help you out. Bye.